Well, thank you, Vanessa, and welcome everyone to this 5G e-seminar. It's likely that everyone watching this has at least heard of 5G, and you probably think of it as the next generation of smartphone communication. This is true, of course, but 5G technology is also enabling and driving some emerging applications in automobiles, manufacturing, and other industries. In this presentation, we want to look at some of the 5G design challenges for these traditional and new markets, and in particular why physics-based simulation is a key to optimal product design. So a quick look at what we'll cover today. We'll start by asking why 5G is so important and why simulation should be at the core of the overall design process. Then we'll look at some business and technical challenges around implementation. At that point, my colleague Mark Rutchland will then continue by looking at some of the major cross-industry applications of 5G. And then finally, I'll wrap up by looking at end-to-end 5G design with the 3D Experience platform. So really, connectivity is the key to modern innovation. And these are some examples of innovation that are shaping the future at the moment. All the way from things like smart manufacturing to the smart city, where multiple data streams are optimizing efficiency and sustainability in real time. And all of these applications you can see here have in common the dependence on electronics and electromagnetics to provide the communication links. None of these would work without a reliable and safe communication channel. In fact, design and innovation in these product areas increasingly relies on electromagnetic simulation. And it's not just electromagnetics either. Other areas of physics such as heat and stress and others must also be considered when you're looking at the overall product design. So at Simulia, we believe we have the solutions needed to address these challenges and the emerging trends and emerging markets. And we give designers the freedom to innovate and virtually explore complex multiphysics design spaces to really come up with the best and optimal overall design. And that means considering every aspect of the design and the associated physics of its operation. So we've seen electromagnetics is at the core of 5G operation, and due to the complexity of 5G systems, which we'll talk about shortly, it will be very hard to design new 5G systems without simulation. So this slide just is a very quick introduction to Simulia CST Studio Suite, our electromagnetic simulation application, and its capabilities for 5G. So we really have 5 broad high-level application areas we deal with in electromagnetics, and the 3 on the right of this wheel you can see in the center here are of most interest for 5G. So microwave and RF up on the top right, that's really about communication and imaging, and antennas are really the core or key enabling technology here. If you go around clockwise, you'll see EDA and electronics, and here we're concerned with the design of circuit boards within electronic devices. For example, signal integrity, getting signals where they should be within a circuit board or IC packaging, and power integrity, getting power to where it needs to be on that PCB or package. And lastly, at the bottom, you'll see EMC, EMI. This is concerned with the susceptibility to outside interference coming in that may affect a device, and also unwanted emissions that may be generated by a product or device. And this is often about meeting geographic regulations. The other areas you'll see on the left of the wheel, these are more specialist areas that we beyond the scope of this presentation, but in particular concerned with motor design and high power microwave applications. So let's look in a bit more detail at 5G specifications. 5G is really a step change in capability from 4G with order of magnitude improvements in many areas. And this is really where some of the challenges and complexities arise, as we'll see on the next few slides. So fundamentally, 5G comprises 3 main pillars. Really, the first one is just the number of connected devices. And over the coming years, there could well be over 100 billion and more devices connected. So that's, each of those devices needs an antenna, some kind of communication channel, so that's an awful lot of devices connecting at the same time. And then the density, 5G is promising much greater density with the ability to handle over 1 million devices per square kilometer. Additionally, the speed specification of 5G is significantly higher than previous generations, up to 10 gigabits per second. This is high enough for streaming 4K video, for example. It's even 10 times faster than gigabit Ethernet, which is the gold standard a few years ago. So this is extremely fast for a wireless standard. And lastly, but also very importantly, 5G is promising ultra-reliable and ultra-low latency communication. So that really means, instant response, 1 millisecond response from when you initiate a request to when you receive a response. That's very important for time-critical applications, as we'll see, and it's significantly faster than even 4G LTE, which had a 50 millisecond response time. So some interesting 5G statistics, and really some of these are pretty impressive. I'll just go through these briefly. Gartner is predicting around 25 billion connected devices by 2021. That's less than 2 years away, and that's a significantly bigger number than the whole population of the world. So you can see there's an awful lot of connected devices coming on stream, and that number is just going to increase over the coming years. Interestingly, there have been over 50,000 technical papers published around 5G, 30,000 of those coming from the top 4 vendors in the 5G space. So an awful lot of research and development going on around 5G standards and specifications and so on. Ericsson has projected that there'll be $3.3 trillion spending on 5G industry digitalization by 2026. That's a large amount of money, and it doesn't even include the consumer market. So that they were, in this particular study, they were looking at industry, as we'll talk about shortly in particular, and they see a very large uptake and growth in industry for 5G. And lastly, autonomous vehicles. This is another subject we'll cover shortly. Intel has predicted that an autonomous vehicle can generate 4 terabytes of data in just one day. If you think about that in a 5G context and you want to start moving some of the processing of that data away from the edge or the vehicle to perhaps the cloud, for example, then you're going to need very fast and high capacity communications to enable that. So let's look in a bit more depth at some of the 5G industry trends and challenges. So some of the technical trends we see are, smaller form factors, everything connected, so not just the smartphone, many other IoT, Internet of the Things type devices, including watches. Some watches are already connected to LTE, 4G, 5G will come over time. We're also seeing very high data rates. So because of the high bandwidth of 5G, the high data rates on the within the product itself are also going to be high, which could cause problems, as we'll see. Low latency, of course, as we just mentioned, and reliability are also key trends that 5G is bringing. And all of this means denser PCBs and packaging, so more circuitry in smaller spaces. And lastly, on the right, we're seeing more antennas, of course. So as 5G comes on stream, legacy communications has got to be maintained. So 4G LTE will still remain in place, 3G, 2G, and so on, in addition to all of the current communications technologies like Bluetooth, Wi-Fi, GPS, NFC, and so on. So an awful lot of antennas being packed into a small space. Some of the business challenges we see for OEMs and suppliers, they really have to adopt 5G technology. If they don't, they'll be left behind in this technology race, and products will become obsolete over time. So it's really critical that OEMs and their suppliers get on board with 5G and start to look at it as soon as possible if they're not already. There's really a challenge in 5G in that there's a step change in complexity. So there's a brand new frequency band being added, which is going to add to complexity, more antennas, as we mentioned, being put into a smaller space. And all of this is giving rise to additional failure points. Also, because of all this, all these changes and smaller form factors, more antennas and so on, generally a redesign has to be completed. So it's not sufficient to take an existing design and just add to it. That probably is not going to work. A redesign of a product is most likely required. There's also an additional challenge about public concern around 5G proliferation due to the number of base stations and just generally the new technology that's coming online. There's certain concerns about that which businesses need to address. Some of the top technical challenges, so we mentioned additional frequency bands, so this is going to be in the millimeter wave band, so millimeter wave technology, which presents a lot of challenges, as we'll see shortly. Component density, this gives rise to a number of challenges, including, for example, like additional heating. There's some new technology coming online called MIMO and beam steering, which is going to increase the capacity of 5G. And we also already mentioned the high data rates, which may cause both interference problems on the product itself, but also externally as well. So one of the major technical challenges is that component placement has to be done correctly. So all of the components, the antennas and so on, have to be placed correctly on the board for it to meet KPIs and safety regulations. And it may be that that there are other areas of physics that are impacted. So, for example, the sensitive nature of some of the 5G components may be affected by a drop or a multiple drop scenario. So that has to be taken into consideration during the design process. Robust design has to be maintained in 5G products. So one specific challenge I just touched on is that 5G is going to operate in two distinct frequency bands. So the first one is below 6 gigahertz, as you can see in green here, and that's a similar sort of band to previous generations such as 4G LTE. And then on the right in blue, this is the new band, and this is the above 6 gigahertz operating around 25 gigahertz up to 40 gigahertz in frequency. And this is the millimeter wave band that we were talking about earlier. So each range has advantages and disadvantages. For example, the bandwidth, you can see in the width of the colored bars here. Below 6 gigahertz, it's relatively narrow at 300 megahertz. When you go up to 6 gigahertz, you get a much bigger bandwidth of 3 gigahertz. And that means a much bigger data pipe, if you like. You can get a much greater amount of data through the communications channel. And that's going to be good for dense environments like stadiums and city centers and so on. One disadvantage of the millimeter wave technology is it's really limited to line of sight, and it's easily blocked by, for example, the human body or the human hand. That line of sight issue can in fact be exploited through reflections of buildings, for example, and in what's called a multipath effect. But fundamentally, 5G products are going to need two systems added to the device. So this is, an extra level of complexity. Millimeter wave also brings new challenges around casing design, material selection, and so on. And just lastly on this slide, you'll see the timeline there at the bottom. So the initial range or set of 5G products will be based in the below 6 gigahertz range, and then the above 6 gigahertz range, which is still actually in the definition stage and the standard stage, will come a few years later. Actually, there's one other point I want to mention on this slide. So in the boxes just above the timeline there, you'll see different frequency ranges for different geographical regions. This is actually an additional challenge because products may have to vary from region to region. Typically, OEMs like to create a world device or a world smartphone, works anywhere. This is going to be an additional challenge because of these different frequency ranges that are set. And in fact, the Dassault Systems 3D Experience platform is a good option here to manage all of this data and ensure digital continuity in managing all of this data complexity. So let's look again at the top challenges in 5G design and talk about familiar solutions in a bit more detail for each one. So as we mentioned, it's really necessary that OEMs and suppliers adopt 5G and what kind of things do they need to deliver? and what's going to help them. Well, as we know, product design cycles in high-tech and specifically smartphones are extremely short. So being able to run quickly and run scalable simulations is very important. Being able to run a complete multi-physics scenario is very important. So not just electromagnetics, but heating and stress factors as well. And being able really to explore the whole design space. So looking at all the variables and being able to optimize across a number of different variables. So really, we're talking about robust early stage product design. That's very critical for 5G and shortening the design cycle. So second major challenge and solution is, the step change in complexity, mainly arising from that new frequency band. So, what do we offer as a solution here? Well, we can simulate 5G systems and the environment complexity. So we're not just talking about components and antennas in isolation, but actually in their real environment. So whether that's within the phone, adjacent to other systems, or whether it's in an environment including buildings or a human body or hand, for example. And also exploring, emerging applications virtually. So looking at not just smartphones, but at some of these new industry applications that we'll talk about. And finally, in the complexity, we really need a platform to manage the data complexity and ensure digital continuity. So we're not just exchanging files, we're really talking about data and digital continuity. And the last challenge and solutions, the redesign aspect. So there are a lot of challenges, a lot of failure points incorporating this new technology. So simulation has got to be able to scale out. Multiple nodes, perhaps cloud, HPC, exploring designs in parallel, exploring a lot of what-if scenarios, and additionally automated workflows so that for each of those scenarios, KPIs, compliance checks are generated automatically and can be collated and analyzed very quickly. So really ensuring robust design, even with many changes in the system. All right, so at this point, I'm going to hand over to my colleague, Mark Rachlin, who's going to continue the presentation.
Hello everyone, hi, I think you can see my screen hopefully. So yes, I'll continue the presentation and I'm going to be talking at a bit more, let's say, technical level, I suppose, because I'd like to talk about how simulation is actually used for designing for 5G connectivity in 3 industries which are of importance, well, for 5G, but of course also for us. Note, these are not the only industries in which 5G is interesting, but there are 3 industries in which it has a big role to play in the future. And that is in the high-tech industry, so for telecommunications equipment, for example, or for mobile devices, in the transportation and mobility industry, and then finally in the industrial equipment industry, where we're thinking about smart manufacturing. I'd like to talk about some of the simulation challenges, but also some of the techniques we use or what can be used in simulation to address those challenges. So if we think about, first of all, mobile devices and their links to each other, I'd say, excuse me for a second, I'm just going to mute you, Jonathan, because you're just there. So if we think about these mobile devices of many sorts, so mobile, phones or tablets, computers, also consumer electronics, maybe communications infrastructure, the key technology that connects all these things is, of course, antennas. So anything that has to communicate wirelessly needs antennas, and since 5G is essentially a communication standard, there cannot be any 5G without antennas. So this is really a primary focus for us. If we then look at antenna design, we're concerned with the entire communication link. So from the cellular infrastructure through to connected devices, be they mobile, so as you're walking around through a city, or whether it's providing a communications link to your house or to your building. Now, as Jonathan said, initially, there will be 2 communications bands, let's say. So firstly, in the existing cellular frequency range, so sub 6 gigahertz, and that'll exist or coexist with existing 3G and 4G technology. But in the future, we'll have dedicated high-frequency millimeter wavelengths, which will provide broadband communication. The key point is that these different frequency ranges require different technology and require different simulation approaches to do the actual design work. So if we think first about mobile devices, so again, thinking about these two frequency ranges, and first of all, the sub 6 gigahertz frequency range at the left, we're basically doing conventional antenna design. But of course, we have more systems, a higher density or complexity of systems within the phone. And so you can't just design, you have to design the antennas with a harmonious coexistence of all the communication systems in the device in mind. And as Jonathan alluded to as well earlier, there's not a single global frequency range which is going to be used. If you look at the Korean or the EU frequency, proposed frequency standards, and compare them to the American or the Japanese ones, there's not that much overlap. So that raises some quite interesting questions for the manufacturer. Do you produce regional devices, or is it possible to design a global device which is able to cater to this extremely wide frequency range then? So if you want to have a global 5G enabled device, at least for sub 6 gigahertz frequencies, can you provide 900 megahertz of bandwidth or antennas which operate across a 900 megahertz bandwidth at a center frequency of 3.7 gigahertz? That is an extremely challenging engineering task. And the key point really is that simulation is essential. And not only simulation on its own, but simulation which makes use of kind of advanced requirement and variant management functionality that the 3D Experience platform brings you. So the context in which you use simulation is becoming more important. The ability to access different variants of a model, and the ability to communicate results very efficiently to your other teams because of the short design cycles that we have becomes extremely important. When we think about millimeter wave, so high frequency integrated arrays effectively, here because the array, the antennas are becoming so physically small, we're likely to see much stronger effects of manufacturing errors and tolerance. So we really have to make designs that are more resilient to things like shifting around mechanically, to thermal deformation. So all of we see a lot of multi-physics effects coming into play. Co-design becoming more important. And this is something that Jonathan will talk about at the end of the presentation. So I'd like to focus on each of these topics in a bit more detail. And I'm just hoping that my presentation is switching to the next slide. There we go. It did crash a bit this morning. In any case, so one of the key simulation challenges at any frequency range when we're talking about these very compact devices is model complexity. Now, an example of this is shown at the left, so kind of an exploded view of this phone with all the different components inside the battery, the electronics, all the different devices like fingerprint sensors and cameras and haptic all of these things have an influence on the antenna design. Accuracy understanding of how your antenna performs, you have to consider all of these parts in your simulation. But of course, that's not possible at every stage of your design process, right? When you're starting off your design process, so when you're doing early stage concept design, because we're running a large number of parametric studies, design space explorations, we have to have very fast simulations. And in order, but still relevant, of course, but in order to have speed of simulation, we need to reduce the complexity. And a key question then is how much detail is still needed? How much can we actually simplify the model in order to still produce relevant results? Because you can't make things too simple. If you make things too simple, the antenna performance will not be predicted correctly, and you won't actually be able to generate a design that can be used in the final device. So an example that I'd like to show you is this one. So this is an antenna in a simplified phone. It's the performance of an antenna. This is a a property of the antenna engineers amongst us, basically telling us how well matched the antenna is, so how well across a variance. Is that we're on the right. You can, the surface currents in the two scenarios, and towards the lower half of the phone, it's frequency performance. So the interaction between the various parts of a complex device are very important. So you have to include enough detail that the simulation results that you get, even for these simplified models, are qualitatively correct, because this is the base for doing the further detailed design work, which is actually going to yield your final antenna design. Now I'd like to talk a little bit about millimeter wave antenna design as well. This is of particular interest in the future, but it's a topic of heavy research currently. And these are really what are going to be, these antenna or chip antennas are going to be what are providing the communication links at millimeter wave frequencies. There are 4 patches on the chip, typically integrated again on the chip, and they have also integrated is the feed network, which provides all the antennas with energy. Now if you integrate this antenna in a mobile device, could be a phone or a tablet, anything else, if you don't take care of the of how you're covering that antenna, what you're going to find is that there's a severe distortion of the way, or a severe modification, let's say, disruption of the way that the antenna radiates. So the far field behavior, so this measure of how well an antenna is radiating in different directions is changed severely. And very importantly, the efficiency drops substantially. So it's something I'll show in a few slides' time. This is something that we have to think about if we want to have these antennas operating efficiently in our devices. And in order to think about this, why we have to understand why, where this disruption comes from. And if we look at an antenna array inside the phone, behind the cover, we can see that, yes, there is some intended radiation on bore side, so perpendicularly away from the phone. But there's also some reflection from this cover, so that's this top layer here. And there's even some energy being guided into the cover and being transported by the cover away from the antenna itself and radiating in unexpected directions. Okay, so what we need to do as antenna engineers is to actually think quite carefully about how this cover is designed, not only the antenna, but the cover above it, how this is designed in order to allow energy to pass unimpeded. Now there are different options possible. 2 of these were discussed recently in an e-seminar that we presented. The link you can find at the bottom of the page. We've also talked about this at some conference presentations. But effectively, by including a window, either an engineered window like the frequency selective, specifically engineered one like the frequency selective surface at the left, or by increasing the thickness of the cover locally to make it easier for energy to pass through the cover. So essentially borrowing radome design techniques from the aerospace industry, we can improve the performance of the antenna greatly. And it's much better than having a simple glass cover. And so the radiation pattern is one aspect, but what's really important and of the greatest interest is the radiating efficiency. So if we look at the left, we're comparing the effect of just a flat cover of a certain thickness, so the standard thickness that the phone had. So is the red curve, and the green curve is if we increase the efficiency locally. You can see that we're improving our efficiency by about 20% across the frequency range of interest. If we then take it further, not only thickening the cover locally, but actually specifically engineering a window, so this frequency selective surface window for the back of our phone, we can improve the efficiency by another 20%, so almost doubling the efficiency. This has an enormous impact because it means that you're requiring much less power to sustain a good communication link. That means that you have a much larger battery life for your device. So even from a systems engineering point of view, it's very important that the antenna engineer has an input or has an influence on the overall phone cover design for millimeter wave applications. Now, that's enough about antennas for this application, but of course they provide the communication link, but the signals that the antenna radiates, so that information has to come from somewhere. If you're receiving information, that has to be processed, and that's done by, of course, the electronics within the devices, which also have to be designed correctly. Now the key point here is that with the advent of 5G, we still have a phone or a device which has the same form factor, but we have more parts, more communication systems, much more densely integrated into the device. Everything becomes more three-dimensional, so you might have more layers of your printed circuit board, you might have folded structures or more flexible printed circuit boards. So everything is more integrated and operating at a higher frequency, and that means that things become more three-dimensional. So meaning that the effect of fields, of electromagnetic field propagation in this compact three-dimensional environment become even more important when we're thinking about quantities like the signal integrity or the power supply integrity. So you need to start doing full 3D simulations and not only simulating at a circuit level. Now, an additional problem that comes in, or challenge, let's say, that comes in when you're adding more systems is that you're reducing the space inside your device. If you're reducing the space, you might well have more thermal issues, so it might be more difficult to cool the device down. And therefore, looking at not only the electromagnetic performance, but also the thermal performance becomes a very important consideration. Whenever we talk about devices used by people, of course, we have to think about safety. So this is something Jonathan mentioned earlier, that one of the key concerns about 5G uptake is what is the effect on exposure to electromagnetic fields. So if we're adding more base stations, also if we're adding more antennas in a device, what is going to be the effect? Are they still safe to use? Now, simulation is used extensively at both early and at regular, throughout the design cycle for antenna design currently in mobile devices, and this is going to increase, if anything. So again, there are two different mechanisms or two different, let's say, approaches or concerns which we need to be thinking about. So at sub 6 gigahertz, the electric field is penetrating quite easily into a person, as shown at left here, and we have to make sure that the energy that's radiated from that phone is below a certain level, right, and is not causing too much of a heating effect inside the person. So the specific absorption rate, this measure of how much power is dissipated inside the human tissue, has to be below certain legally specified limits. At 28 gigahertz, so at millimeter wave frequencies, we don't really have a very deep field penetration into the surface. That doesn't mean that there's no safety concern. So all that energy is being dissipated in a smaller layer of the skin, also at the surface of the skin. So you still have to be quite careful that you don't have too high energy levels in that smaller volume. Right, but we don't look at the typical SAR parameters anymore, which are typically in a 1 gram or 10 gram volume of the human tissue. But there, what's going to be the case is that we're going to look at the power levels on a surface. So power flow on a surface is shown here, or perhaps the power flow on the surface of a representative part of the human body, like the head or the arm. Very importantly, and this is something that can't be compromised on, is that since you're talking about these safety relevant quantities, the accuracy of the simulations has to be extremely high. So we can't just have simulation speed, we have to have simulation speed, but not at the cost of accuracy. So just to focus, to look at each of these very briefly, in the classical communication band, so sub 6 gigahertz, we have standard CTIA head and hand models, which are used in compliance testing, are included with our simulation software. And of course, by using, in particular, our time domain solver technology, we can simulate the fields on the surface, the fields inside the person, and derive these compliance testing relevant quantities like the specific absorption rate is shown here. So this is pretty standard. Now, when we move up to millimeter wave, we have an additional challenge. So you have the same issues of safety and the effect on coverage, but the big question becomes, how do you model a head or a human body at 28 gigahertz or at these high frequencies? And the reason that's a question is because of the wavelength size. So if you look at the wavelength of the electric or electromagnetic field at 28 gigahertz, in free space, it's 10.7 millimeters roughly. If you go into the human body, which has a permittivity or relative permittivity, which is in simulation, or for these homogeneous body models, it's taken typically as about 40, that reduces the effective wavelength to about 1.7 millimeters. And that means that a person of 1.7 meter height is 1,000 wavelengths in size. That becomes quite a challenging large simulation model. And the approach to use, because we're not that interested in the fields inside the body, as we saw earlier, the fields don't really penetrate inside, we can model effectively not model the interior of the body. So we can use it, we can make that for example, a perfect conductor and model that just with a coating around the outside, which has the properties of skin. And then, of course, the other question is, so let's say we can model the body, but how do you model this finely detailed phone in the context of the body? And here we use a hybrid simulation technique. In fact, you could almost say that it's required. So we simulate the fine detail of the phone, perhaps with the surrounding hand, with a full wave technique like the time domain solver. Then we record an equivalent field source and use that as an excitation for a second simulation step where we're using perhaps again a time domain approach, but maybe also a more numerically efficient technique like the integral equation solver, so a method of moments approach, or even a shooting bouncing ray approach embodied by us in the asymptotic solver. Now, the effect of this hybrid workflow is to hide the fine detail of the phone from the large model simulation. So it makes it possible to simulate accurately, but at large scale. And then you can understand, yes, okay, so we have the phone on its own, is radiating a certain way, but what is the effect of the hand on the radiation pattern? What is the effect of the user on the radiation pattern? And that becomes an important consideration, again, when you're thinking about looking at the overall system view. Just focusing on the hand briefly, so one of the benefits, or one of the things that being able to simulate at high accuracy with a human body makes possible is to look, for example, at what is the effect if a user is holding a phone in a certain way, is that going to be prohibitive? So is it going to have an effect on the radiation pattern? In this case, on the left, we're blocking the antenna slightly, but it's still radiating quite well. And on the right, we're not blocking it, and it's radiating even better. But this could, for example, guide the antenna engineers or the phone designers to understand how many arrays do I need to place in the phone to ensure a good communication performance in all directions, regardless of how, or for let's say average use by a cross-section of users. And by the way, as just seen, so this is described in a lot more detail in this webinar that we had last year, which is linked to here and can be viewed on demand. Just a brief word, and this is not the focus today, but of course antenna design on the other side of the communications link is equally important. So we have this, these key trends in base station design are that, again, we're going to be using higher frequencies, but also even in our lower frequencies, we're going to be switching to using more antennas, so using this multiple input, multiple output type of architecture. Beam forming and beam steering becomes increasingly important. We're having larger arrays, and they're going to not only be, they're going to have hybrid digital analog feed architectures. We're going to have integrated access and backhaul nodes, which will enable this millimeter wave densification without straining the core network. And a very important point is that the designs of these new antennas have to be manufacturable. So we can't get too unconventional because that becomes expensive. And so keeping things manufacturable is going to be an important, let's say keeping the costs in control is going to be an important performance characteristic or an important constraint if we're going to achieve this desired network densification given the constraints that we have. And of course, in the infrastructure, so the base station infrastructure is not only related to antenna design. Infrastructure needs to be protected against lightning strike, against electromagnetic pulses, but also against things like earthquake or wind. So if on the left here you see the exposure of a base station to the electromagnetic pulse, which we can understand by simulation. On the right, we see the wind velocity around a large building, so the Petronas Towers in this case. So simulation allows you really to not only do the antenna design and the component design, but to understand what's going to happen to those components when they're placed in the real world, as Jonathan mentioned earlier. So that was the bulk of my talk. I'd like to briefly talk about some topics in automotive 5G. Again, simulation, of course, critical to enabling future mobile connectivity. But here one of the interesting things that we're able to simulate at quite large scale. So a key question, will vehicles be able to communicate with other vehicles and the environment, but also will the person in these vehicles, like in a bus, in a car, be able to have a communications link? And then, of course, it's not only an electromagnetic question, but we have the multi-physical aspect or the multi-domain aspect. Will that communications link, which might be critical to maintain, will this still work if you have spray or mud or snow that is being kicked up by you driving through an environment? Is that going to cover the sensors and prevent them from working? And if we can understand that sort of effect, then we can say, okay, well, maybe we need more sensors, more antennas, maybe we need them to be positioned differently to avoid having these problems, or perhaps you need to change the design of the vehicle to keep the locations where your communications infrastructure is safe. The systems behind the antennas, again, also need to be designed with 5G KPIs in mind, so key performance indicators. So are they being designed with this requirement for higher data rate in mind? Will all these electronic systems, which are even more now, work in each other's presence? And of course, then we have kilometers and kilometers of cabling in a vehicle. Will these allow the high-speed data transfer that we need, or do we need to start looking at other questions like maybe a wireless communications link? And as I mentioned just a moment ago, what happens if you have, dirtying of the car, but also what happens if you have physical damage? If you're crashing and you're relying on the kind of the real-time reliable link to communicate that to emergency services, will those communication systems still work after a crash? So for this, we need multidisciplinary simulation, and this is what we, of course, can offer. For antenna design in particular, we can really look at all aspects of the 5G communication design, from the design of the antenna itself, its placement on the vehicle, so to understand where it should be placed, how many antennas we need perhaps, looking at the radio frequency interference between all these devices, and of course then the performance of the electronics itself. Now, to wrap up or to finish with, I'd like to talk a bit more about antenna placement, but in the context of smart manufacturing. So this is an extract of an ebook which is available on our website about the future of manufacturing, but I'd like to point out two terms. So smart, of course, meaning implying sensors, so something to record data, but also interconnects. And this, of course, implies antennas. And so given that we have to design antennas and place antennas and sensors throughout our smart manufacturing environment, and given that those have to be designed by simulation, we can really say that simulation is going to be transforming this industrial experience as well. Now, one example, an interesting example, is from a recent study done by Ericsson and the Fraunhofer Institute. And they were investigating the potential of 5G to improve the manufacturing of bladed discs, so BLISCs for short, which are key components in aircraft engines. Now, high construction accuracy is absolutely essential. Now, the problem is that to make such a bladed disc, this is done by milling. so as shown kind of or indicated at the left, but it takes quite long to do this. So it could take more than 24 hours. And the problem is that there are unpredictable vibrations that cause sort of small deviations or defects potentially in the Blisk geometry. And because these are, because of the high required accuracy, what happens is that there's about a 25% rework rate. So 25% have to be discarded or have to be changed afterwards. And this is, of course, an extremely expensive undertaking. Now, these vibrations can be measured. And one of the ways that is being considered to improve or to reduce this rework rate is to actually measure the vibrations in real time, thanks to the low latency of the 5G network, communicate information about the vibrations to a control system, which can then, via the 5G network, the locally installed one, and then communicate information to the CNC milling device, which can in real time compensate for those vibrations. And using this, it's estimated that we could have a 10% reduction in the rework rate, which could lead to enormous savings. So the estimate of the study was that 5G, just enabling 5G just for Blisk manufacturing, could save about 360 million euros annually. Now, from a simulation point of view, of course, what we're interested in is how do we decide where to place the antennas for these communication modules so that the entire system works. And an example that we have here is of an industrial robot. And here we're comparing the positioning of two antennas, or an antenna in two locations, one high up on the structure, one low down on the structure. This looks quite simple, but actually there's several things that are required here. So you need an antenna, of course. You need an antenna design that you want to position, but you also need an accurate model of the robot. Not only of the robot, but you need an accurate model of how this robot moves, what positions it's likely to be in, and the environment that it finds itself in. So if we have that, and we do have that because we have access in real time effectively through the 3D Experience platform to all this information, we can then run some simulation studies to see how the antenna performs when it's in different locations. So here's the antenna in the high location and in the low location, and we're looking at the electric fields in a two-dimensional plane, the same two-dimensional plane each time. You can see that there's quite a difference in terms of where it's communicating to. But in order to really understand how the communications link might be affected, we need to not look at this in 2 dimensions, but 3 dimensions. So here we're comparing the directivity, so essentially the 3-dimensional radiation performance of these antennas. And at first glance, they might look quite similar, but if you look a bit more closely, you'll see that the left one is actually quite distorted. And you'll see that there are these kind of nulls appearing, or areas of poor radiation in this direction here, in this direction here. In this direction, it's a bit more strong. So the question then is, if you have an antenna in this position on your robot, and the robot happens to be in a position where your base station or your access point, your 5G access point, is in the direction of poor radiation, what's going to happen to your communications link? It might well stop working. Right? And so what you have to do is, this sort of information allows you to determine how many antennas do I need on my robot, or for a particular operating behavior, how many different access points do I need to place to ensure this continuous, reliable link to the industrial equipment, to the robots that are operating in our environment. So with that, it might have taken a bit longer than I was supposed to, but I'd like to hand back to Jonathan for the conclusion then. I'll just hand over to you, Jonathan, to make you the presenter again. There you go.
Okay, thank you. Thank you, Mark, for that. Yeah, just before I start, I do want to encourage you to type in a question if you have any into the Q&A dialogue in GoToWebinar. We may have time at the end just for 1 or 2 of those. All right, so yes, I mean, as Mark has alluded to, and there's different applications he's shown, connecting all the physics is very critical for 5G. So, you need to consider the electromagnetics. Obviously, you've got to consider thermal, making sure the device stays within thermal limits. You need to consider mechanical simulation, particularly for smartphones and handheld devices. They get dropped a lot, so how is that going to affect not just things like the screen and the warranty issues and the robustness of the device. How is it going to affect the antennas and all of the critical components that are placed inside? And then, of course, the industrial design as well. It's got to still look good. It still has to be functional, even though with all that additional technology. So Dassault Systems has tools that can deal with all this. It can manage the data. There's a tool shown in the middle here called Process Composer, which can help you with multidisciplinary optimization, design of experiments type studies, and so on. So really, connecting the physics is critical, and to bring simulation as close as possible to reality, and to explore the complete design space. So how do you go about doing that in a sensible fashion and making sure it really is accurate? Well, there are different ways to bring physics together. One of them is called co-design or sequential design. This is maybe where you do an electromagnetic simulation that causes a heating effect, which then causes a structural deformation, perhaps. And then those are kind of sequential, so one follows the other. The deformation at the end, that does not reflect back to the affecting the EMAG or the electromagnetic simulation. So it's just one sort of cause and effect type sequence. But then maybe that structural deformation at the end does impact the electromagnetic performance. So you need to do a full co-simulation, as you can see on the next image over on the right here. So you do the electromagnetics, then you do the thermal, the structural. The structural is actually maybe changing the position of some components, which changes the electromagnetic performance. So you need that complete cycle simulated. And then right over on the right-hand side of this slide, you can go even further and start to look at full design exploration. So all of the different variables, you can run them in parallel, perhaps, look at multidisciplinary optimization, so not optimizing just across electromagnetics, but optimizing across lots of different physics as well. So all of this is going to help you explore the very large design space of 5G and really get very accurate results and end up with the ultimate or the optimal product design. So really, Dassault Systems, just to summarize, it has a unique value proposition for 5G. You can accelerate 5G innovation, using the tools that we've talked about and using them on the 3D Experience platform. So Dassault Systems expertise is really cross-industry. We've talked about high-tech, transport, mobility, and industrial applications in this webinar, but we cover many other applications too in consumer products, life sciences, aerospace and defense, and so on. And some of those may also be impacted by 5G innovations. And as we mentioned a little bit earlier on in the presentation, managing all of the complexity of 5G is very well suited to the 3D Experience platform. And you can see a graphic of how that sort of is represented on the right here. It's the complete end-to-end product chain. So the 3D Experience platform can manage all the way from the market analysis, upstream thinking, ideation, through to design, optimization, validation, and then downstream to production, delivery, and even to the marketing aspect as well. So really the full end-to-end process, and that's very important for such a complex area such as 5G design. So I want to wrap up this presentation with just some key 5G takeaways. So, main point is OEMs and suppliers, they really must spend on 5G development to stay competitive. That's really not a question. 5G design is complex and there are many points of failure. So all of those have to be considered to get a robust and optimal design. Really early stage design exploration is going to be the key to making sure that the final product is right first time. Making sure it meets KPIs, making sure it's compliant with regulations. And there are many traditional and emerging markets for 5G. So as Mark talked about, high-tech mobile communications, of course, but also additional emerging areas like transport mobility, where you've got data telemetry going on, industrial equipment, manufacturing halls, and so on. So, just to conclude, we believe that Dassault Systems offers fast, accurate, scalable, multi-physics and multi-scale solutions for end-to-end 5G design.